Hi everyone, this is the beginning of the second topic, mg5004 and the corresponding DE paper. This is topic 2, class 1. Any real number can be represented by a point on a number line, whether they're rational or irrational. We could have 3 over 2, that's rational. We could have root 2, we could have pi. All of these can be put somewhere on here, like 1.5 could be put there, for example. Negative 3 over 2 could be put there. We can also represent intervals on a line. If we have a look at the left-hand side here, these open circles here between negative 6 and negative 4 tell us that x is somewhere between negative 6 and negative 4, and that we could write that as an open interval. If we look in the middle between negative 1 and 2, we can see that we are including negative 1, and we are including 2. So in that case, we'd write it as a closed interval with square brackets on both sides. The third interval between 3 and 4 is open at the 3 end and closed at the 4 end. So that means we don't include 3, but we do include 4. So we can write it open at that end and closed at that end. Now, what we're doing here is still doing just a collection of tools that later on we'll get to use properly. Some terms that you probably know but just need a reminder of. A reciprocal is where you invert it. So say if you've got x plus 4 over x minus 5, then the reciprocal would be x minus 5 over x plus 4. The modulus is the size regardless of the that doesn't make sense, regardless of the direction. So remember, there's the proper definition there that it equals itself if x is greater than 0, and it equals the opposite of itself if x is less than or equal to 0. Sometimes it's useful, particularly in a branch of mathematics called permutations or combinatorics. This idea of factorial, you can actually use the calculator. There's a button on your calculator like that, and that will help you. Saves your brain. I'm sure you remember or recall that you're not expected to learn all of the Greek alphabets, but it just is, it's a good way of thinking, oh, I wonder what that squiggle means. Ah, that squiggle, there it is there, and looking up what it means. So the common ones are the alpha, beta, gamma, delta, epsilon, theta, lambda, mu, omicron, pi, psi, omega, maybe phi as well, tau, and rho, and I guess sigma as well. So just if you see a squiggle, just think, oh, that must be a Greek letter, and look it up. Just some words that you need to remember as well. Product indicates times, quotient indicates divide, numerator is on the top of a fraction, and denominator is on the bottom. Something like x plus 2 over x minus 7 is just an expression. There's no equal sign, so you can't solve it ever. Then the delta notation, that's useful later on when we look at partial differentiation, just means a little increment. The sigma notation, and in this case it tells us that we're looking at the first term and we're going to add them all up until the fifth term. And scientific notation is where we have one digit and we adjust using powers of 10. Standard stuff here, just some examples, some things that you really need to remember. If you're multiplying and they've got the same base as a, then you can add the powers. If you're dividing, you can subtract. If you're taking a power to a power, then you multiply. A to the 0 is 1, a to the negative m is 1 over m, and I'm not sure that you can see at the bottom that a to the m is equal to 1 over a to the negative m. Now, really be careful with these. Something like that is 5x to the, because that's a 1, so that would be 5. But 5x to the power of 4, the 5 has to be to the power of 4 as well, so it would be 625 x to the power of 4. Similarly, 5x squared to the power of 3. Right, the 5 has to be cubed, that would be 125. The x has to be to the power of 2 times 3, which is 6. Something like 5x to the power of negative 4. The 5 has to be to the negative power of 4 as well, so that would be 625 on the bottom. It would be x to the 4 on the bottom and 1 on the top. More rules of powers, this time for fractions. Sometimes you need to simplify something like 1 plus root 2 over 1 plus root 6, and to do that you would multiply by 1 minus root 6 over 1 minus root 6, and you just use FOIL, and what you do is you end up with a number on the bottom line. So if we multiply that out, on the bottom line we're going to have, because that's the difference, a fraction plus, and sorry, bracket plus and a bracket minus, so that would be 1 plus 6, so that's going to be over 7. And on the top line we're going to have 1 times 1, which is 1, minus root 6 plus root 2, going to run out of space, minus root 12, and I'll write that down here. If I need to simplify, I could say that that's 1 minus root 6 plus root 2, and I could write root 12 as square root of 4 times 3, which is the square root of 4 times the square root of 3, so that's 2 root 3. So then I could put plus 2 root 3 in there. Just a few examples. 32 to the power of a fifth. The power of a fifth, that means the fifth root of 32, which you can count on your fingers, would be 2. 32 to the 2/5, using the rule at the top of the slide, that would be the 5th root of 32 squared. Or it could be the 5th root of 32 squared. Either way, you'd need to look it up on your calculator. Just going over the distributive laws, that this is a times b plus a times c, and the same for subtraction if it's a times b minus a times c. And it makes no difference whether the letter is at the end, the variable is at the end, it's still c times a plus c times b, or c times b, and there. So that would be AC minus BC, and AC plus BC for the top one. You also need to be able to not just look at a variable outside a bracket, you need to be able to look at a bracket times a bracket. You can either learn how to do that, you can learn that it's a smiley face, or you can remember it by using the FOIL rule, so that you multiply the firsts together, the outsides together, the insides together, and the last. So it's the first, outside, insides, and then the last. And that just reminds you how to do it. Factors go hand in hand with products. A product is what you get by multiplying two factors together, but sometimes it's more useful to go the other way, to take the product and actually factorize it. So if we look at the first example here, a is in both terms, so we can take a outside the bracket. A times what is a squared? It would be a. There's a plus sign there. A times what would give us 3ab, and the answer would be 3b. The second lot of material on the page just reminds us of some special factorizations or expansions, depending on which way you're going. So a plus b all squared. Now this is one that students get all the time, so just make sure you remember it. And a squared minus b squared is the difference of two squares. And the last one is how you go about completing the square if you need to. If we are looking to factorize something like 5x squared minus 7x minus 6, we need to remember that it's all to do with finding two numbers that multiply to make -6 and two numbers that multiply together to make 5 and that combine to make -7. If we set up the factors of 5, there aren't very many, and then we set up the factors of -6, so we've got -6 and 1, so that's 5x and x. -6 and 1, 6 and -1, 3 and -2, and -3 and 2. What we'd have to do is we'd have to try pairs until we got the right answer. I know what the answer is, so I'm just going to skip to it so I don't take up too much space. I'm going to choose 5x and 3 and 1x and -2. So there's my bracket, 5x plus 3 and x minus 2. Now, if I hadn't chosen that one, if I didn't know what the answer was, if I'd chosen something else, I would need to check. So let's check. 5x times x is 15x squared minus 10x plus 3x minus 6. And when we do the business, that is indeed correct. What if we had something like x squared minus 1/9? How would we factorize that? What we'd do is we would recognize that it was a square minus a square. So we'd use the difference of two squares rule to say that that is going to be x and x, and then it's going to be the square root of 1/9, which would be 1/3, and one bracket will be plus and the other bracket will be minus. Have a look at these diagrams. These diagrams are a very clever way of proving, if you needed to have proof, the idea of a plus b squared. We've got it on the left-hand diagram. We've got a plus b by a plus b. So we could write that as a plus b squared. And look at what it's made up of. It's got a squared plus ab plus ab plus b squared. So that's plus 2ab plus b squared, which is what you know. But what we're doing here is we're using geometry to prove that, if you needed it to be proved. The next one is another proof. It's a little more complicated, but it works. Again, we've got a plus b by a plus b, so a plus b squared. And if we look at how it's been divided up into little bits this time, we've got 4ab plus a little bit in the middle, a minus b squared. Now suppose we want to find ab. So let's shift the a minus b squared. Now we're nearly there if we just divide both sides by a quarter. So we can do all sorts of things there to prove various facts. Pascal's triangle is just a very famous way of being able to expand lots and lots of brackets. It's a pattern that goes on forever. You can see what the pattern is. You look at this row here. So if we go into the next row, all the way down the outside, it's going to be 1. And then 1 plus 4 is 5, 4 plus 6 is 10, 6 and 4 is 10, 4 plus 1 is 5, and then another 1 down the other side. So we can just go on writing out expansions, as many as we like. Remember that division particularly is the tricky one, and it asks us how many times does C over D in this case go into A over B. So it's the old flip and multiply. The multiplication example there, top line times top line, so that would be 12x to the 4 over y squared z, and we couldn't simplify that. The next one we could simplify because we could cancel one of those 5's in there, and in actual fact then that's our answer. What about if we did something like this? This is nasty. 14a squared b over 3c4d5 times 9c6d over 21a4b3 times 12a squared c over 20b squared d4. Wow. Actually, it's not that bad. It's going to be 14 times 9 times 12. And then there's going to be it's going to be 4 A's. And there's going to be 1 B. And there's going to be 1 C. And there's going to be 1 D. And on the bottom line, we're going to have 3 times 21 times 20. And we're going to have 4 A's? No. How many A's have we got on the bottom? Just 4. Yep, 4 A's. And how many B's have we got on the bottom? We've got 2, 3. We've got 5 B's on the bottom. And we've got 4 C's on the bottom. I think we've missed some C's on the top. That should have been 6 of them there. And what else have we got? Oops, no, that's not where it should have been. Should have been 6 there and 1 there. That's 7. That's what it should have been there. And 4 on the bottom. And how many D's have we got? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 on the bottom. So if we do the numbery bits on our calculator, we end up with 6 over 5. Now I'm thinking that the A's are going to cancel. One of those B's is going to cancel with one of those, so we're left with B to the 4. I'm thinking the C's, we've got 7 on the top and 4 on the bottom, so that would be 3 on the top. And we've got D's, we've got 1 on the top and 9 on the bottom, so that would be 8. So just to remember, you do algebraic fractions just the same as you do with numerical fractions, except that you've got variables. Stop the video now and do these, and then just check your answers, that the first one is going to be negative 3x minus 4 over 40. The second one is going to be b over 5a times a plus b. And the last one is going to be 30 over a. So don't just look at the answers, do it first. Let's just do these briefly. It would be 4y minus 3 times x plus y over x plus y times y. So it would be 4y minus 3x minus 3y over x plus y times y. So 4y minus 3y would be y minus 3x, going to run out of room, over x plus y times y. Similarly for this one, it would be 2 times x minus 1 plus 5 times x plus 3 over the common denominator of x plus 3 times x minus 1. And if you're careful and take out your brackets carefully, you end up with 6x plus 13 over, oops, I didn't show, x plus 3, x minus 1. Now the last one we could find the common denominator as being x minus 4 cubed, and then the first one has to be multiplied by x minus 4 squared, and the second one has to be multiplied by just 1. And then if we factorize that, we can see that we're going to end up with x minus 4 times x minus 4 plus 1 and the x minus 4, one of them can cancel with one of them, leaving a 2. And on the top line now, we've got x minus 4 plus 1, which would be x minus 3 over x minus 4 squared. Standard stuff, just the rules to remember. You can do anything you like when you're rearranging a formula, as long as you do the same to each side. Let's have a look at something that's a bit nasty. So we'll have a look at qt equals pi d squared l n over 4. And let's rearrange this to find L. So first up, we'd multiply both sides by 4. Now we divide both sides by everything except L. And then we have what we were looking for. So we've now released L. L is equal to 4qt over pi d squared n. Now L is the subject. Up here, qt is the subject. With this kind of question, it's absolutely imperative that you draw a diagram so that you can see what you've got. We're starting with a cylinder that's got a radius of 6 and a height of 15, and we're melting it down into a shape like that. So the volume of the cylinder is going to be pi r squared h, so that's going to be pi times 6 squared times 15, which is going to be 540 pi, and we'll give it a unit. Now we're going to lose 8%, so 92% of 540 pi is the volume of the new shape. So that's the volume of the hemisphere plus the cone. So whatever that is, 0.92 times 540 pi. Okay, these are some basic things that you know. The volume of a sphere is 4 over 3 pi r cubed, so the volume of a hemisphere would be just half of that, and the volume of a cone would be 1/3 pi r squared h, and that's got to equal this 0.92 times 540 pi. Let's make it easy on ourselves and divide right through by pi and tidy it up from the first term. Then we're going to get 2 over 3 r squared plus 1 over 3 r squared h is equal to, still, we haven't worked it out, times 540 pi. We're told that the diameter of the new shape has to be 12, so we know that r must be 6. So we can put all that in. So we now know that 2 over 3 times 6 squared plus 1 over 3 times 6 squared times h is going to be, I'd prefer just to still leave it as 0.92, but let's just write it down so we can see what it actually is. 2 over 3 times 6, nope, that should have been a cubed. 2 over 3 times 6 cubed would be 144, plus 1/3 of 6 squared would be 12. And then if we just rearrange so that we've got 12h equals 352.8. Now this must be now centimetres, and h must be therefore that divided by 12, which would be 29.4 centimetres. So draw your diagram, put in things that you know, and then just gradually work your way through to find what you've been asked to do. Again, draw the diagram. I have done it for you, so let's just start. A boiler consists of a cylinder. It's got a hemisphere on the top, and it's got a cone at the bottom. Find the volume. Okay, let's do it in bits. The volume of the hemisphere is going to be 1/2 times 4 over 3 pi r cubed. And if we look at the bit in the diagram, the radius is 3. We add that bit up, so it'd be 18 pi centimetres cubed. Now we do the volume of the cylinder. Oops. That's pi r squared h, so that would be pi times 3 squared times, look at the picture, it's 8, so that's 72 pi meters cubed. The volume of the cone is going to be, now the volume of the hemisphere is P, the volume of the cylinder is Q, the volume of the cone is R, and the volume of the cone would be 1/3 pi r squared h, so that's equal to 1/3 times pi times 3 squared times, now look at the picture, look at the diagram, times 4, so that's 12 pi meters cubed. So the lot, the volume of the boiler, is all of that added together, and when you add up the bits, 18, 72 and 12, you'll get 102 pi meters cubed, or if you wanted it in an actual number, you're also asked to find the surface area. So the surface area of P is going to be 1/2 times 4 pi r squared, which would be 18 pi square meters. The surface area of Q would be 2 pi RH, and that's 48 pi. So that's the cylindrical bit. The slant height you can work out, it's actually a Pythagoras triangle. It's a Pythagoras triangle that's 3, 4, 5. So the slant height is 5. So L is equal to 5. So now we've found L. And then the surface area at the bottom then, the surface area of R would be equal to pi RL, which would be 15 pi meters squared. So adding them all up, the total surface area would be 18 plus 48 plus 15, which would be 81 pi meters squared. And if you needed a number, would be 254.5 square meters. I don't think that's your textbook. Page 20. But it's an open container and it's made from a sheet of cardboard 200 millimeters by 300 millimeters, just by folding up the sides. And you need to show that the capacity is x times 300 minus 2x times (200 minus 2x). Okay, that's the initial one. So it's the area of this bit here folded up into a box. Okay, let's now play with that. That's in cubic millimeters. Let's change it to milliliters. And what we're needing to do is to find this in milliliters. So what we're going to do is we are going to divide it by 1,000 and take out some factors as well, because we've got common factors in there. We've got 300 minus 2, 200 minus 2, so we could take out a factor of 2 twice, so that would give us 4x out the front, leaving us with 150 minus x times 100 minus x, and we're dividing it by 1,000. Okay, that looks pretty straightforward. Just divide the 4 and the 1,000. So now our final answer would be x times 150 minus x over 100 minus x over 250. We'll do this question in class. It's a bit long to do here. Then we move on to the next chapter and we're looking at functions. Function is just a rule. You put something in and you get something out. And something happens in this thing in here, and that's all it is. A function is just something that takes an input, spits out an output. Look at this very simple example here. The function in the middle says add 2 to the input, and out pops x plus 2. So if we were to put in 2, what pops out? We add 2 to the input, so it must pop out as 4. What happens if we put in negative 2? We're going to add 2 to that, and out pops 0. What if we put in a half and add 2? Then we'd get out the other end 2.5. So a function is really just the mathematical expression for the way that the value of one quantity, which is the dependent variable, depends on the value of another, which is the independent variable. Often, as you'll see here, we use x for the independent variable and y for the dependent, but not always. But if we do use x as the independent and y as the dependent, then we say that y is a function of x. That is, it depends on the value that you choose for x. So we could say that y is a function of x, and that's not multiplication, it's notation. It doesn't mean f times x. We can graph functions. In this particular one, what we're looking at is the fact that -2 is less than or equal to 2, which is less than 2. So we're only looking, actually, I think we might be looking between, no, look at it again, between 3 and 3. Sorry, I had my hand on it, I couldn't see. So we're looking at it where x is between -3 and +3, and we've got a function that is x squared plus 2. Let's look. The domain is the set of x values. It's the independent values, and in this case the domain can take any value from -3 to 3, and the range, so that's the set of independent variables, and the range is the set of dependent variables. And in this case, the range goes from 2 right up to 11, and it can include both of those. Common thing is for people to say that the range is 9. No, it's not. The range in this sense is between 2 and 11. Sometimes we just need to be a little bit careful of a function that might be something like y equals 3 over x plus 2 squared. It's going to have a gap in it because x can't equal -2. Why not? Because the bottom line would be 0, and we can't have 0 on the bottom. Now, if you know or have access to MATLAB, you could use MATLAB to draw graphs, or you could use a really lovely piece of website, I think, rather than a piece of software called Desmos. Both of them draw beautiful graphs if sometimes it's a bit tricky for you. We can have more than one function operating at a time. Suppose we've got two functions, g and h, and what we're looking at here is that there is a difference in the order of things. In the example number 1, we've done g first, and it squares the input. Then h takes that, multiplies it by 3 and adds 5, and we spit out 3x squared plus 5. In the second example, you treble the input and add 5, because we're going to do h first. So we spit out 3x plus 5. Now our function g says square the input, so we're going to spit out 3x plus 5 squared. We can actually also do a function on itself. So suppose our function f said, take your input x, multiply it by 3 and add 2. So that's 3x plus 2. And then we put it into the, if you like, f machine again, which says multiply the input by 3. So that's 3 times 3x plus 2, and then add 2. Now you could leave it like that, or you could simplify. But looking at it like that, you can actually see what happens. This is the first bit of f in here, in there, and then you do it again. So you get multiplied by 3 and adding 2. Sometimes it's useful to do this translation from the maths, say 3x plus 5, into treble the input and add 5. Now, a function, a special meaning of the word function is that an input has a unique output. Now, if we look at the function here, take the square root of, it gives us two answers. The square root of 4 is both 2 and -2. So it's got two answers. And if we were to draw it with these Venn diagrams, 4 is mapped onto 2 and 4 is mapped onto -2. So if we want a description of that, we say it is 1 to many. And 1 to many cannot be a function, this thing with a unique output. It doesn't have a unique output. This particular relationship doesn't make it into a function because you've got two answers. If we were to graph this function, take the square root function, have a look at it down at the bottom in the graph down here, you can see that for any x value, it has two y values. So if we could generalize that, we could say that if we applied a vertical line, talk about the vertical line test, it's going to cut the relationship in two places or more. In which case then it's not what we call a function. It's not special enough. For the input, it's got two outputs. This example, though, is not the same. The function down here we see in the diagram here is y equals x squared. Each input has only one answer. -3 only has 9 as the answer. 3 has only 9 as the answer. Now, if we're going to apply the vertical line test, look at it here on the graph. A vertical line is only going to cut the graph in one place. So this is what we call many to one. And it is a function. So it is a function. Y equals x cubed is a function. It is 1 to 1. And if we were to use a vertical line test, we'd find that it only cut the graph in one place. So this is a function. It's special enough to be a function. We can model voltage. This is a picture of some voltage. We can model voltage using a sine function. It is a function. It's not just a relationship, it's a function. It's special enough to be called a function because for each x, there's only one y. Anywhere we try it, for each x, there's only one y. So it again is 1 to 1, and it is a function. It's special enough to be a function. Something like this is not a function, it's simply a relationship. Have a look at these ones. If you look at question A, graph A, and you apply a vertical line, look, 1, 2, 3, 4 y values. Over here the same. 1, 2, 3, 4 y values. It's not a function. If we look at the bottom picture, it is a function. Because if we say, look, every x value only has one y. Every x only has one y. So for each x, there is a unique y. And that's what makes us, this is what gives us the idea of a function.